Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska, Fairbanks. Today I want to talk about the solution to problem 4 in the practice final exam. This section deals with climate and climate change. A. Which of the following describes a negative feedback mechanism? A negative feedback mechanism is one where a mechanism kicks in that weakens or opposes an initial change. It doesn't necessarily cause a positive change or a negative change. It can cause either, but the point is it just opposes the initial change. A positive feedback is a mechanism that acts to reinforce or amplify an initial change. Negative feedbacks are essentially things that keep a system stable. If you create a change and a negative feedback kicks in, it will return us to its original conditions. A positive feedback is a condition where you will get things changing and then the changes being amplified further along, and so it's an unstable situation, if you will. B. If the Earth were in a cooling trend, which of the following would be a negative feedback mechanism? So if the Earth for some reason is cooling, let's say the Earth is traveling through an asteroid cloud that reduces the amount of sunlight reaching the Earth, what would cause a negative feedback? What would cause the Earth to warm against the cooling trend? If we decrease the amount of carbon dioxide, we're going to push the Earth towards further cooling because we're decreasing the greenhouse effect. If we increase the snow cover, we're also going to have further cooling because we've increased the albedo and reflected whatever sunlight is finally making it through to us. If we decrease the amount of cloud cover, that would be a negative feedback because that would increase the amount of sunlight reaching the Earth's surface and try and make the Earth warm against the cooling trend. And decreasing the water vapor content in the air, that would be a positive feedback, just like decreasing the amount of carbon dioxide would be a positive feedback in this case, because decreasing the amount of water vapor reduces the amount of greenhouse gases and allows the Earth to cool further. So the answer is 2, that we are in a cooling trend. A negative feedback is something that stops the cooling, and we can stop the cooling here, or at least reduce the cooling if we reduce the amount of clouds, because then we let more sunlight get to the ground and warm the planet. If the Earth were in a warming trend, which of the following would be a negative feedback mechanism? And the answer here is increasing the amount of cloud cover around the globe. If we increase the amount of cloud cover, we increase the albedo of the Earth, we reflect sunlight to space, and it doesn't warm the Earth. Increasing the amount of carbon dioxide in a warming trend just adds to the warming. It's a positive feedback. Decreasing the snow cover around the globe also allows the Earth to warm. And increasing the water vapor also pushes the Earth towards more warming, so that would be a positive feedback in a warming trend. The increasing the snow cover around the globe and decreasing the snow cover around the globe that we've looked at in B and C here give you hints of the role of snow cover in cooling and warming trends in terms of amplifying an effect based on surface albedo that we'll come back to later. From 1949 to 2005, the meteorological record shows that temperatures in Alaska have increased with step changes over the 56-year period. And this is of importance that what we understand as the warming trend in the late 20th century is not just observed as a steady bathtub increase that you might expect from just the temperature rising uniformly around the globe, that climate change is complex because we have synoptic changes where low and high pressure systems move just as they do in the seasons. They also, in a changing climate, might shift and therefore cause abrupt changes as they shift, as opposed to steady, gentle changes just because the amount of carbon dioxide has increased in some general way. Polar amplification, E, is primarily due to which of the following processes? And it's due primarily to ice albedo feedback, and we'll discuss this later. Volcanic eruptions cause cooling of the Earth's climate, and that's a general effect all around the world. It isn't particularly polar. Changes in the Earth's orbit again affect the whole Earth. They're not anything special to the poles. Increased concentrations of greenhouse gases aren't special to the poles. They will tend towards warming all around the world. But because in the polar regions ice exists, we live in the cryosphere, if you will, a place where water can exist as ice, which is bright, shiny, high albedo, reflecting sunlight. When it melts, the ground is revealed, which is generally lower albedo, or the ocean is revealed with lower albedo, and so you flip from a high albedo world to a low albedo world as ice melts, and back again as the earth cools. And this can act as a positive feedback mechanism, whether you're warming and you get an albedo decrease, or whether you're cooling and you get an albedo increase. We're going to talk about temperature as part of climate around the planet, and I'm going to turn to the diagram while I talk about the questions. Here we see a map of isotherms on the Earth's surface, lines of constant temperature in degrees Celsius, and you notice up in North America it's slightly obscured, but we've got contours of 10 degrees Celsius and 15 degrees Celsius that head up into Alaska. And so for a monthly average temperature, is this January, March, July, or September, an average temperature of 5 to 10 degrees Celsius in interior Alaska is indeed the month of July. The next question, we're going to identify, we have 1, 2, 3, 4, 5, 6 boxes here identifying climate control processes or their effects on the temperature map, and we have 6 questions, so we want 1 question per box. Don't use any box twice. And so it's asking you to make priorities if you're uncertain about which box should go with which process. Land, sea, water distribution is A. Because we're in the summer hemisphere, we know that the land will heat more than the ocean. It has a lower heat capacity, and so we see the temperature contours in A go far north over land, but not so far north over the ocean. So if I travel out from northern British Columbia to the Gulf of Alaska, the temperature is steadily cooling, and that's an example of land water distribution controlling climate, that the climate along the coast is cooler than the climate in the interior in the summer. B, a cold ocean current in the northern hemisphere is the classic case of B, where cold water comes down out of the Gulf of Alaska along the coast of California, and we see that 15 degrees Celsius contour pushing south along the coast of California as cold water comes south. Critical to the climate of California that cold water off the coast is controlling the amount of moisture that comes in to the American Southwest and contributes to the desert regions of the American Southwest. 3. Four. A cold ocean current in the southern hemisphere, and the example is the Peru current, where the 15 degrees Celsius contour is being pulled northward along the coast of Chile and Peru. Again, this is also part of the fisheries in Peru, that current heading northward along the coast causes upwelling in the ocean and nutrient-rich waters which feed the fisheries off the coast. It's those fisheries being disrupted that led people to identify the El Nino pattern. 5. The control of latitude on temperature. The best example here is C. If latitude controls temperature, it controls temperature because of the angle of the sun in the sky. The sun is lower in the sky at high latitudes than low latitudes. If there was no other control on temperature, the isotherms would all travel perfectly east-west, and it would just get steadily cooler as we go from the equator to the pole. And that's what happens in C. As we head towards Antarctica to higher latitude, we just have horizontal lines of temperature that we just cross. As we go to higher latitudes, it just gets steadily colder. That's the control of latitude on temperature. 6. The control of elevation on temperature is seen here in the contours over the Andes. The fact that we have the 15 degree Celsius contour heads all the way up to where the 25 degree Celsius contour is over Brazil, and that's because at high altitudes the atmosphere is thin, therefore it's easy to get radiative cooling at night, and so we have very cold temperatures. There isn't much atmosphere keeping us warm. There's very little greenhouse effect. And finally, low cloud cover. The 30 degrees Celsius hotspot in the southwestern United States in July is associated with low cloud cover in the American Southwest It's also where we are 30 degrees approximately north and south. We're in the descending side of the Hadley cell. We have the high pressure systems that occurred there and give us clear skies at high temperatures, so we have deserts around the world at 30 degrees north and south. If I turn now to G, we're looking at precipitation map of the Western Hemisphere. Dark green is high precipitation, light green is low precipitation, and we ask questions about the influence of different weather systems. Again, we have 6 choices and we've got 6 boxes. So taking it from the top, the influence of high and low pressure weather systems on water, and in this case that is the effect of the Azores high or the Bermuda high sitting off the coast of the southeastern United States, and in the circulation of that high pressure system it brings water in from the Gulf of Mexico in over the southeastern United States and keeps it quite moist in the southeastern United States. The influence of prevailing winds, the example I would give here is B, Washington State. Winds generally flow from west to east at mid-latitudes and therefore carrying moisture in off the Pacific into Washington State. The effect of latitude and the general circulation on high precipitation is the high precipitation in Amazonia in Brazil is E, where we have intense convection and thunderstorms all through the afternoon, and the intertropical convergence zone passes over Brazil. In 4B, identify cold ocean current in the northern hemisphere contributing to precipitation, and the example is C, the cold ocean current coming along the coast of California. Even though there's moist air coming in from the Pacific, the dew point temperature of that air has to drop as it passes over the cold ocean current and therefore heads on inland, having lost a lot of its water vapor. There's fog along the coast, famously at San Francisco, and then dry air heading inland to the very dry climate of California and the American Southwest. Identifying an area where there's a cold ocean current in the southern hemisphere is F, along the coast of northern Chile and Peru. We have a cold current that again reduces the humidity of the maritime air coming off the ocean so that dry air heads inland. C and F are examples of where we have coastal deserts, which may seem as a oddity or counterintuitive, that we can have regions of the world in Australia, in Africa, in South America, in North Africa, and in southwestern United States where we're next to ocean but we have deserts, and it's because of these cold ocean currents drying the air before it comes on shore. Finally, an area that best illustrates the influence of mountains on precipitation, I pick A, our own Alaska range. Anybody who's driven the Parks Highway or the Richardson Highway has seen this very effectively as you cross from the dry interior to the wet south central Alaska. It's important to point out that B also has the Cascade Mountains in the mix, that those winds coming ashore in Washington State also hit mountains, and it's talked about in the book. And all I'm asking you to do here is say, okay, picking between them, they both have mountains in the mix, but the wetness of the Pacific Northwest is just due to the endless amount of water coming in on those westerly winds, effectively all year round, but particularly in the winter, into Washington and Oregon from the North Pacific. The final part of the exam, H in problem 4, what is ice albedo feedback? Briefly explain how it contributes to polar amplification. Polar amplification is where in a cooling trend the polar regions cool more rapidly than the rest of the planet. Ice albedo feedback, first of all, is a positive feedback mechanism where increasing ice cover increases the albedo at the ground, so reducing the amount of solar energy absorbed in the ground because it's more reflective. So cooling the ground, so you increase the amount of ice, so you increase the albedo, so you cool the ground, so you increase the ice, you increase the albedo. There is a climate scenario of if a planet begins to get cold and ice is over, does it go into, if you will, a death spiral of ice because of ice albedo feedback, that the cold surface is reflective and therefore encourages more coldness, and so we amplify the initial cooling, and can you get into a weird situation where that runs away and you trap a planet in an icy condition because of ice albedo feedback. Why does it contribute to polar amplification? It contributes to polar amplification because the poles are the region in the current climate where we have significant amounts of ice cover all year round in Antarctica and seasonally in the Arctic. And so in the poles, we are in the cryosphere where snow and ice are common due to the cold temperatures. Ice albedo feedback is very important in polar regions. As the temperatures cool, the albedo increase due to increased ice result in amplifying the amount of cooling, and so we have amplification of a cooling trend in the polar regions. So if the planet as a whole is generally cooling, the cooling becomes more emphasized in the polar regions because with that cooling comes increased ice cover. There might be ice cover in the shoulder seasons in the spring and fall, and that ice cover reflects sunlight and causes those regions regionally to be even colder still. So we have polar amplification. In a warming trend, because the ice melts, the albedo changes rapidly in the other direction, and so now we get increased warming in the polar regions. And so polar amplification works both in a cooling phase as ice grows, but also works in a warming phase as ice decays. And this is also reflected in breakup in Alaska, that once you melt the ice in April and get rid of the snow, the ground is much darker in color, a much lower albedo, and once melting happens, it takes off very aggressively once you melt through to the ground. So we see that effect both locally, but we're seeing it as a climate effect in the Arctic, that we do measure more rapid warming in the Arctic than elsewhere on the planet in the current warming phase.